So next, we've got Tianshi Gao. And Tianshi is a principal AI scientist at Cruise. And his talk is titled Cruise Predicting the Unpredictable with Cruise's Continuous Learning Machine. Over to you.
Yeah, thanks, Shiva. So hello, everyone. So my name is Tianshi. I'm a principal AI scientist at Cruise. So today, I'd like to share with you about how we predict the unpredictable with Cruise continuous learning machine. So here's the outline that we're going to cover today. So first of all, I'm going to give a quick intro to Cruise, and then we're going to hello. Okay, sorry, I think I'm hearing someone asking me to wrap up.
No, I think you've got another window open. We can hear you.
Oh, okay, great. So should I restart since we are recording?
You're okay. You can continue.
Okay, thanks.
No problem.
Okay, so this is the outline. I'm gonna give a quick intro to Cruise, and then we're gonna deep dive into the prediction problems and its challenge and some of the key insights. And then we're gonna actually take a close look at Cruise continuous learning machine and how it is applied to solve the prediction problem. So who we are. Cruise is a San Francisco-based self-driving company building the world's most advanced self-driving technology. We're actually on track to be the first company to go driverless in a major US city. We're tackling the biggest technology challenge in our generation in order to provide a transportation option that is safer, more efficient, and more accessible for everyone. So in other words, we're working to disrupt the status quo of transportation today. In particular, there are actually 40,000 people die in car accidents in the US alone every year. And 94% of these crashes are caused by human errors. Our goal here is to remove the error-prone human driver from the equation. Secondly, the current transportation is not green at all. In the US, transportation makes up the largest share of greenhouse emissions. In addition, peak hour commuters actually will waste a week of their lives in traffic. So for San Franciscans last year, 116 of those 290 hours were spent in traffic. That's longer than the average vacation. So our answer to these big challenges is the Cruise Origin, the world's first production-ready, all-electric, self-driving shared vehicle. It is purposely built with no driving wheels and pedals, but yet with safety as a top priority in mind in order to provide smooth, safe, and accessible transportation. The Origin is also fully electric and powered by 100% renewable energy, as is the rest of our fleet, which means it can decrease both congestion and greenhouse gases. But to do this is not easy. So here is what's like to drive in the downtown area of San Francisco. What we are seeing here is a first-person view from the Cruise car. So in order for us to navigate such a chaotic scene safely, we first need to perceive and understand what and where are the objects around. And then we need to actually predict what they're going to do next, such that we can then plan what we're going to do safely. So let's actually dive into the prediction problem we just briefly talked about. So what is prediction again? So let's look at a simple example to understand it. So what we are seeing here is a bird's eye view of the world. This is an intersection with four-way stop signs. So this white car here is the Cruise car. And this is the car that we're most interested in this particular example. In this case, the cruise car wants to drive straight, but when it should go is in fact a function of what this oncoming car is going to do next. So for example, if this oncoming car wants to go straight, then it has no interaction with the cruise car, so both can go simultaneously in parallel. However, if this oncoming car wants to turn left, then because it arrived at this intersection earlier, we should yield and wait for it to clear. So this is exactly what we're trying to do, as shown in the bottom graph. So this green curve shows our estimation of the possibility of this oncoming car going straight, and this yellow curve shows the probability, the estimated probability of this oncoming car turning left over time. So at this particular moment, we're seeing that given the orientation of this car, both going straight and turning left are both very likely. But in a few moments, we can see that the car started to turn, and you can see that our prediction about this car starts to favor turning left. And as a result, we're going to wait for it to go first. So to summarize, the prediction problem is really just about understanding other road users' intent and then predict their future motion such that it can drive safely. So let's also look at another interesting example. The other interesting example corresponding to to another intersection that is slightly more complex. So what we're interested in understanding here is that we wanted to understand all the different kind of driving patterns at this intersection. Specifically, each blue point in this graph indicate a position of the car we observe at a particular point of time. So if we accumulate the observation over time, you can see that the cars tend to follow the lanes. And this black region is simply indicating a specific exiting lane at this intersection. So what we're interested in is that we're interested in those driving trajectories that start from somewhere at this intersection, but ending and exiting from this specific lane. And here are some observations about the patterns. So first of all, as we can see, a majority of the driving trajectories are basically driving straight. It starts from this lane and it ends and exits from the same lane. And then we are seeing a much smaller number of trajectories that starts from a different lane and did some lane change sometime in the middle and then exit in the adjacent lane. Similarly, we're also seeing a small number of trajectories that corresponds to a long left turn. Perhaps what's most interesting are these two U-turn trajectories. These are, in fact, in some sense, the most challenging prediction problem. For example, based on this kind of data, you can imagine that we can write a very simple rule to make prediction. The simple rule basically says that all the cars is going to just follow their lane and drive straight in the next couple of seconds. And it can probably be over 90% right in this kind of real world data. But they're going to fail badly for these two U-turn trajectories. Let's look at another example. This corresponds to actually a mid-block. As you can see here, a majority, almost all the driving trajectories are actually straight and following the lanes. Even though it's extremely rare, but there do exist two U-turn trajectories in the mid-block. And then these are actually the trajectories that we need to predict safely in order to be better than human. So now we understand the long tail prediction challenge. Before we dive into the continuous neural immersion idea that tries to solve this problem, I'd like to first highlight a couple of key insights that are important to make the continuous neural immersion possible. The first is that the prediction problem in self-driving is, in fact, a self-supervised learning task. The reason for this is that the future always reveals itself over time. So in historical data, we actually know eventually what actually happened. And in retrospect, we can use those observations to construct a label and train the model. So the second is that active learning for self-supervised tasks is actually free and can be done at scale. This is because for every instance, both the prediction and the label are readily available. You can easily basically compare these two and then find interesting example for the model to improve. So the next insight I would like to highlight is actually the data. We all know that ML models are only as good as the data. What's nice about driving in San Francisco for Cruise is that our cars get exposed to challenging scenarios that are orders of magnitude more often than, let's say, some suburban areas. In particular, you can see from this table where we are comparing basically the number of maneuvers per, let's say, unit miles driven between two locations. One is San Francisco, is the other is Phoenix. As you can see, for example, the frequency that we actually see construction navigations between San Francisco and Phoenix is that San Francisco actually has almost 40x more densities, frequencies than Phoenix. So this is actually a foundation for us so that we can build a machine learning based model to predict these long tail maneuvers. Okay, so let's put all these elements together to build the continuous learning machine. Let's say we start from the simple model, which basically predicts that every car is going to drive straight. Let's deploy this model on the car and let's start driving in chaotic San Francisco areas. So at every single moment of time, this model is actually going to make a prediction for every object the car sees around it. And we can just wait a little bit and see what's actually going to happen. And then we can then compare what we predict and what actually happened to find a mistake. So for example, in this case, we may find trajectories that are doing U-turns. Now after finding these error samples, in this particular case, they are all auto-labeled because the future reveals itself. And then we can then augment our existing training data with these error samples. And then we ask the model to fix these mistakes by training it again. And then we evaluate and hoping that this new version of the model at least can do better that the previous model made and overall achieving higher accuracy. And then when we deploy this model again and ask it to make predictions again, and we find the new mistakes. So what's nice is that over time, hopefully this model is going to focus more and more on those really, really challenging and long tail scenarios. And then finding those, train on those, and then improve. So this is basically the continuous learning machine cycle. And we can just repeat this loop without human intervention automatically. And then hopefully the model can just continue to improve, especially for those long tail challenging scenarios over time. So does this work?
Sorry to interrupt you. Can you make your screen bigger? People are having a hard time seeing this. Can you just like expand your screen a little bit? Your presentation.
Is this better?
More. It's still very small. Much better. Much better. Oh, you had it there.
Okay. So I maximize it. Let me see. Okay, I'm gonna maximize the window. Does it work now?
Yes, it looks a lot better now.
Okay, great. Yeah, sorry about that. So yeah, let's look at whether this works. So this is one specific example. On the left, you can see that this white car is the object of interest. So what this car actually did is that there is a parking garage, and this car actually did a cutting from 2 lanes apart to this parking garage. This is not a very frequent kind of maneuver or trajectory you're gonna see. So initially, our model was not timely enough. So this graph on the right-hand side shows the prediction at this particular moment in time for this car, and these are basically the future position that the model estimates. After doing one iteration of COM, and for this specific instance, you can see that it can now correctly understand that, oh, yeah, there is a parking garage here, and we need to basically predict that this car is gonna turn and cutting into the parking garage. We also talked about the U-turn examples earlier, and this is a real-world prediction for it. As you can see here, this car is the object of interest, and this is a bird's eye view of the same car. This blue curve is basically our prediction. As you can see that the model did a very good job to predict this U-turn trajectory very early on. So it picked up the sign that this car is just driving slightly to the right, which is a discriminant signal that this car is actually gonna do a U-turn. So here's another example, which is what we call U-turn. So in real world urban driving, you will actually, even though it's pretty rare, you will actually see people just turning around in front of us in the middle of the road, where you can see that like the car is gonna reverse and then and move forward. In this case, our model actually did a very good job to really understand this pretty rare and complex maneuver. The other example I would like to kind of highlight a little bit is the prediction for a car that goes around a front obstacle. This is actually, this seems to be kind of easy for human, but it's actually a hard prediction task for machine learning model, because it really needs to understand the scene very well. In this case, as you can see that our model actually did a pretty good job to predict that this car is actually gonna use a different lane to go forward. So lastly, continuous learning machine is actually right now powering the 2 million autonomous miles driven in San Francisco. So this is a video that we recently shared, corresponding to a 75-minute full autonomous nonstop driving. And you can basically find this video, full video, on Cruise YouTube channel. Yeah, so that's pretty much it. Thank you, everyone. So if you have any questions, I'd be happy to answer them.
Thank you, Tianshi. That was great. Very cool slides. And sorry we weren't able to. I I should have told you earlier to increase the size of your slides, but it's great. Okay, so looks like we have a couple questions. One is from Yuchi Oda. CLM seems to solve a lot of problems. Is there a problem you can't solve?
Yeah, like I mentioned earlier, the machine learning model is only as good as the data. There could be actually scenarios where only you can see once per, let's say, 1,000,000 miles. So those are the kind of problems I think requires a different approach to solve.
Okay. And then the next question is from Shijian Li. Do you have a human in the car and drive all over the San Francisco while the autonomous car makes predictions?
Yes. So more specifically, we actually have two kind of what we call autonomous vehicle test operators presenting in the car. They are actually gonna they actually let the car to drive autonomously. And if there are, let's say, dangerous situations that they think the car is not gonna be successful, they're actually gonna take over so that it can be safe. And then sometimes it will drive manually. But in all these modes, the models are making predictions, and we're basically collecting basically training data.
Okay, great, thank you. We've got another question by Yuchi Oda. Thank you. What insight into human judgment could improve the trajectory prediction at a certain location?
I'm not exactly sure. So what this means, do you mean like, so if we think about how humans make predictions, what kind of information or like information can use to improve prediction? Is this is what this question means?
I'm not sure. That's all they've got there, but let's go with that. Yes.
Oh, yeah. Okay, yeah. So yeah. Totally. So yeah. So let's say actually, kind of in some sense, feature engineering or maybe signals is one part where human can share a lot of intuitions. So for example, like let's say we talk about the go around kind of maneuver. So as a human, we actually understand that because there is a static obstacles in front, and then the car, in this case, the car will need to go around. So by understanding how human reason about that, when we build the machine learning model, you can imagine like that we need to, let's say, add, let's say, feature channels corresponding to, let's say, the object around the target object. And then maybe let's say we also need to further classify that whether, let's say, an object around is static or not. So yeah, definitely like there is a lot of human intuition that we can leverage to improve the model.
Great, we have a few more questions, so let's get through them. Can you comment on which ML methods are being employed?
Yeah, unfortunately, I can't talk about the details here, but probably I can say like it's powered by deep learning.
Deep learning. Can you give any more details there? What kind of deep learning?
Yeah, unfortunately, I don't think I can kind of provide more details. Yeah.
Okay. All right. Next question is, what are the ballpark size of the data being handled every second or every minute?
Oh, yeah. So that's a great question. So, for self-driving cars, actually, it operates, most of the self-driving cars, they operate at 10 hertz. So meaning like for every second, there are going to be 10 kind of, how do I say, snapshots about the world. So you can basically imagine like it's the average number of objects around you per snapshot, and then times 10. So that's basically the ballpark kind of size we're talking about here.
Okay. We'll skip the next question from Dud, and we already answered a question he had. Let's go to Vinod's question. very cool work with continuous retraining of models. Sometimes stability can be a problem. In CLM, what helps maintain the stability of the models? E.g., it does not go into an unstable cycle.
Yeah, this is a very insightful question. So yeah, there are tons of probably small details that needs to be taken care of to ensure that it is stable and it's
Hello,
not
everyone. We have Paul Barba,
Sorry, ignore that.
Chief Scientist.
Ignore that. Sorry, that's another session. Keep going.
Yeah, totally. So yeah, indeed, like there is a risk of the model, let's say, being not stable or maybe even converge into some kind of bad local optimal. So yeah, so there are various considerations here. So one is, for example, the data, right? So maybe you probably don't want to always only train on like only the mistakes from every iteration. Otherwise, your model is going to be overly drifting to a specific error distribution. Instead, maybe you wanted to consider, let's say, kind of the normal distribution as well per iteration. So in some sense, you don't want to probably, let's say, throw away like the older distribution. Other things like you probably wanted to be careful about in some sense kind of regulate the model and also the learning rate, things like that. So they all need to be taken care of. Yeah.
Great. So we are out of time. There is another question on instability. How do you avoid instability in the model? I mean, it's similar to the one you just answered. Learning one prediction, then having to subdivide the prediction into multiple use cases. If you could answer this quickly, because we're over time for our next session.
I'm not exactly sure I fully understand this question. I guess probably one thing I wanted to comment, maybe it's related, is that in real world applications, the prediction is not going to be a single point estimation. There are inherent uncertainties in this world. And in order to drive safely, you probably want to consider multiple possibilities. So in fact, what I didn't show here is that, the detail I didn't show here is that the prediction model actually output a distribution of possibilities. It's not a single trajectory. So from that perspective, there will be a certain flavor of, let's say, robustness or stabilities. So maybe this is helpful. Yeah.
Great. Thanks very much, Tianshi. That was really great talk. Thank you, everybody, for all your questions.